MIT, NASA, and other astronomers have found a new way to measure how fast a black hole spins, using the flickering results of a star feast. The method takes advantage of a tidal disruption event, where a black hole exerts tidal forces on a passing star and tears it apart in a super bright moment. When a star gets disrupted by the black hole's immense tidal forces, half of the star gets flung out, while the other half gets pulled into the black hole, forming an intensely hot accretion disk made up of the rotating star material. The team led by Mitch showed that the wobbling of this newly formed accretion disk is key to calculating the natural spin of the central black hole. In a study published in Nature, astronomers reported that by tracking the pattern of X-ray flares produced immediately after a tidal disruption event, they could measure the spin of a nearby supermassive black hole. The team followed these flares for several months and determined that the flares likely signaled a bright, hot accretion disk wobbling back and forth as it got tugged by the black hole's own spin. By tracking how the disk's wobbling changed over time, the scientists could figure out how much the disk was affected by the black hole's spin, and thus calculate how fast the black hole itself was spinning. Their analysis showed that the black hole was spinning at less than 25% of the speed of light, which is relatively slow as black holes go. Dheeraj D.J. Pasham, a research scientist at MIT and the lead author of the study, says this new method could be used to measure the spins of hundreds of black holes in the local universe in the coming years. If scientists can study the spins of many nearby black holes, they can start to understand how these gravitational giants have evolved over the history of the universe. Pasham, who is part of MIT's Kavli Institute for Astrophysics, says astronomers could, over the next few years, use this method to work on various systems and predict the general distribution of black hole spins and understand the long-standing question of how they evolve over time. Co-authors of the study include collaborators from NASA, Masaryk University in the Czech Republic, Leeds University, Syracuse University, Tel Aviv University, the Polish Academy of Sciences, and several other institutions. Each black hole has a natural spin shaped by its cosmic encounters over time. For example, if a black hole has grown mostly through accretion, where material briefly falls onto the disk, it can spin up to quite high speeds. Conversely, if a black hole has grown mainly by merging with other black holes, each merger can slow things down as one black hole's spin counteracts the others. As a black hole spins, it also drags the surrounding spacetime along with it. This dragging effect is an example of a long-standing theory called lens-Thirring precession, which explains how extremely strong gravitational fields, like those produced by a black hole, can pull the surrounding space and time. Normally, this effect isn't noticeable around black holes because the massive objects don't emit light. However, in recent years, physicists have suggested that during events like a tidal disruption event TDE, scientists might have the chance to follow the light from the star debris as it gets dragged around. Then, they might hope to measure the black hole's spin. During a TDE, scientists expect that a star can fall onto a black hole from any direction, forming a disk of white-hot, shredded material that might be tilted or misaligned with the black hole's spin. Imagine the accretion disk as a tilted donut spinning around a donut hole, which has its own separate spin. When the disk interacts with the black hole's spin, it wobbles as the black hole tries to align it. Eventually, as the disk settles into the black hole's spin, the wobbling decreases. So scientists predicted that the wobbling disk in a TDE should be a measurable signature of the black hole's spin. Pasham says the key was having the right observations. The only way to do this is to get a telescope on an object right when a tidal disruption event happens and keep looking at it continuously for a long period, from minutes to months, over the past 5 years. Pasham has been searching for tidal disruption events that are bright and close enough to quickly catch and follow the signs of lens-Thirring precession. In February 2020, he and his colleagues got lucky with the detection of a 2020 CN, a bright flash coming from a galaxy about 1 billion light-years away, first spotted in the optical band by the Zwicky Transient Facility.